Good morning, students. So today we will be talking about elasticity, and in this particular lecture we will be talking more about stress and strain, their tensor characteristics and related concepts. So last week we looked at how some of the elastic characteristics are related to the atomistic structure of the material, and based on that we were able to calculate and predict what should be the elastic modulus of the material, and also what would be another property that is directly related, the thermal coefficient of thermal expansion. And we also saw that these two are related to the atomic bond energy and the steepness of the bond. Okay, so moving on, today we will be talking about elasticity, stress and strain. So content-wise, what we will be discussing today is, you can find in chapter 1 of Hosford and Cadell. This is the book that I have already informed you is my go-to book. Hosford and Cadell. The book name is Mechanical Behavior of Materials. And another book that would be useful in understanding these concepts is The Mechanical Metallurgy by Dieter. So what we need to understand is the basics of stress, strain, elasticity, and plasticity at the macroscopic level. So in this context, so what we need to understand are the stress, strains, macroscopic meaning one level higher than what we have already looked at, which was the atomistic origin. So we will now come out at a little higher, or in length scale it is larger, much larger than the atomistic scale. When we are dealing with the overall bulk characteristics, you can say, and trying to understand these behavior, elastic and plastic behavior at the bulk level, then we need to keep few things in mind. One is that the assumption, there is an inherent assumption when we talk about these characteristics, and that is of continuum mechanics. You may have heard this term. What do we mean by continuum mechanics? What we mean is that there is no discontinuity in character. So if we are talking about stress from one point to another point to another point to another point, then we are assuming that there will be a continuity. It is not that at one point it will be very high, other point it will be very low. There is no discontinuous function of stresses and strains, which in turn means that when we are looking at the macroscopic model, we are assuming that there are no atoms, or basically the material is distributed uniformly throughout. And hence the characteristics that it represents are also uniformly distributed. Uniformly meaning not that the overall characteristics become homogeneous, but that atoms are, or the material, the atom or the mass is not concentrated in atoms, but it is distributed. And then hence you get a continuous property of the material. So this is one very important thing to keep in mind. Now we have already looked at the concept of stress, and we said that stress, although it may be very familiar concept today, but it was not so easy to understand at some stage. But now we understand it to a good extent, and for now we will consider it as force per unit area. Where Fn I am representing to represent force acting normal to the given area. But there are shear stresses, which are basically forces acting in the plane. Strain, this is change in length per unit length. Now the strain can be defined in 1 dimension, 2 dimension, or 3 dimension. So it is not that here, for simplification, we have kept delta L by L, which means it is a single dimensional, but you can also have strain in 2 dimension and 3 dimension. And another important concept to remember while we are moving ahead right now is that whenever we are applying stresses on a material, then there are two distinct regimes. One is the elastic regime and the other is the plastic regime. In the elastic regime, the material regains its original shape, while in the plastic regime, there is a permanent shape change in the material. So right now we are talking about the elastic properties of the material. So always keep in mind whether we are in the elastic or the plastic regime. And as you would see as we go on, that elastic regime, you have much more exact and accurate equations to define relation between stress and strains. But when we move on to the plastic regime, that equations become more vague, more complicated, and they are not very accurate, to put it simply. Okay, so coming to the concept of stress. Let's say we have a free body, something like this, which is constrained at one region, and then it is also constrained at another region like this, and there are some loading that has taken place over there. Okay, so complex loading. It need in a real life application, we know that the loading would be very complicated in nature and not a simple uniaxial loading. So let's say this is how the loading condition is on the material, which is fixed at these two regions, and then there is a load here, and then there is a load here, and it is still very simple. But even in this simple condition, we will not be able to go and uniformly define the overall stresses. Okay, so there will be a continuously varying stresses over the whole body. So what we do is we take or define the stress at a particular point, or what is called as state of stress at a point. So let's say this is the particular point P. So this is the point P, and we want to understand the state of stress. What is the state of stress at this particular point? So in order to understand this, what we do is that we will assume one, we have already said continuum mechanics, and now we will assume that this because the material is very, you can say, continuously varying characteristics, so we can assume that we can take one cube type of structure from there. And when we talk about the state of stress, we will be defining the state of stress for that one particular cube. So let's say this is the point we are talking about. So it's a very, very small cube that we have taken from this particular point, and infinite number of such cubes which will fill this whole bulk to make up this component. And we can define the state of stress for each and every of these cubes. So it is a cube, although it has not come out very accurately. And then we can say, okay, first that there will be these axes. So let's say this is x-axis, this is y-axis, and this is z-axis. In a general condition, there will be state of stress. So there will be shear stress. These are the shear stress. This is normal stress. Similarly, there will be a normal stress here, and there will be shear stress along these. These are the shear stresses, and this is the normal stress. So overall, this is how the stresses in a general condition would look like, and we will come back to this to understand more about it. But for now, this explains how the state of stress is defined at different regions. So this is one point, there can be another point, and the values would keep changing at each and every of these points. In the most simplest of the cases, it may remain constant, but given the loading condition, we can say that it will keep varying. Now, to understand it in a better way, let's look at a simple example. So let's say you have a bar kind of shape like this, which is standing vertically and which has dimensions A and B. And let's say we have put a brick over here. Whose weight is W equal to mg. Now, since this body is not deforming, so an equal and opposite force must be acting in this direction, which is equal to F. Therefore, F is equal to W is equal to mg. So mg is the force acting onto the rectangular bar, and F is the force which is equal to mg is the force acting as a resistance from the bar. So what is the state of stress on the surface here? So that can be given as follows. The stress on top surface can be given by sigma. Assume that this is y direction. So sigma yy, and we'll say we'll come to why it is called sigma yy. Sigma yy equal to force per unit area. The force acting is W by area is A into B. So this will be the stress acting on the material or acting on this on the surface, and this is acting normal to the surface over here. In other cases, as we would see, it may even act on the plane. So under what condition? We'll see. So for example, let's say now we want to talk about on a different plane inside the material. So let's say we are interested in this particular plane. Okay, so because we are talking about state of stress, and we looked at those very small cubes, and those cubes fill up the whole material, and we can define a stress of state in each of these cubes. So we can also look at one particular plane. So over there also there are several of those cubes, and we are looking at the state of stress for that particular cube in that particular plane. So here we will take the section which is given here, which will look. So if we take away this section, cut this bar at this particular plane, what we will have is a section like this. So here you will have some force. This is the force which was acting in this particular direction. And now there will be components which will be acting, one normal to this particular plane, so we can call it Fn, and then one will be in the plane, which we can call shear or tangential. So for now I will call it tangential. So this is the force acting over here, and this is our angle theta. So the plane is inclined at an angle theta. Remember that F is a vector. So at any given angle theta, we can find what will be the force Fn and Ft. So let's write down those. Fn, which is equal to basically W or mg, is at an angle theta. So this is the angle, this is also equal to angle theta. Therefore, Fn can be, since it is a vector, it can also be given as Fn equal to W into cos theta, and Ft is equal to W into sin theta. Okay, so we have now resolved the force components in normal and tangential direction, but now we also need to find out the area over which it is acting. So what is the area over which it is acting? So this area is the same. So we will not define it as An and At, it is A theta. So A theta is equal to A by cos theta. Now, once we have the forces and the area values, then we can calculate what will be the sigma along this normal direction, which is the stress in the normal direction, and stress in the tangential direction, which is called the shear stress. So this is not the normal x and y. So we will define it as y prime, and this one will be defined as x prime. So what it comes to sigma y prime, and again we will explain in a few minutes why it is called sigma y prime, and not just sigma y. So this is sigma y prime, and this is normal. So the force acting is Fn, and the area is A theta. So it becomes Fn was equal to W cos theta, and A theta is equal to A by cos theta. So this becomes W by A cos square theta. But W by A we already have calculated is sigma yy. So this becomes sigma yy times cos square theta. And the tangential one, which we are defining right now as y prime x prime. So this is the shear stress. It is F tangential by A theta, which will be equal to W sin theta divided by A by cos theta. So it will become W sin theta cos theta, and W by A times sin theta cos theta, and W by A is sigma yy. So this becomes sigma yy sin theta times cos theta. Now, why do we define the stresses as two subscripts? So when we say sigma ij, there are two subscripts I and j. What is their significance? I defines plane. I defines the plane, and j defines the direction. Direction of what? Sorry, here it is plane. So the two terms have been defined as I defines the plane, j defines the direction. So here when we are saying y prime, it means we are talking about the y prime plane. So you can see if this is normal y prime direction, so this becomes the y prime plane. And when we are talking about normal force, so force is acting in normal direction. So it is acting perpendicular to this y prime plane. This is the y prime plane, and the force is acting perpendicular to this. On the other hand, y prime x prime, it is still acting on this y prime plane, but the force is in the x prime direction. So it becomes sigma y prime x prime, and that is how it is defined. That is why we have two subscripts. And in fact, as you will see in the next slide, that you will have possibility of 9 different components. Okay, so now that we have an equation here, let's think about what will happen at theta equal to 0 and theta equal to 90. So what we see is that if you put in the equation for this one at theta equal to 0, cos 0 is equal to 1. So sigma y prime is equal to sigma y. What does that mean? That means that we are looking at the original stress where the force was this original condition where the force was acting on the surface. So theta equal to 0 is very simple, but then let's also put the theta equal to 0 in this equation, which is y prime x prime. So here sine theta term is there. So when you put theta equal to 0, then the whole thing becomes 0, which means the tangential or the shear stress is 0, which means that in this particular condition, we had no shear stress, which also is true. So theta equal to 0 is very easy to understand. Now let's put theta equal to 90. Now when we put theta equal to 90, what happens to this first equation? Cos theta at theta equal to 90. Okay, let me just write this square term properly. So when you put theta equal to 90 in cos theta, it becomes 0. So this term is 0. And here sine theta is equal to at 90. Sorry, here also you have one cos theta term. So here also this term will go to 0. So what happens at theta equal to 90, your normal stresses as well as shear stresses are 0. So how is that possible? Both normal and shear stresses are going to 0. What is the meaning of this? So you think about it. We will come back to it. We'll answer that question in a moment. So with this basic understanding of stress, let's define the stresses as tensor quantity. Okay, so we will look at stress as tensors. So we will again go back to our cube. So let's say this is the cube. On which the stresses are acting. So this is used to define the stresses in all the 3 different directions, x, y, and z, and the normal and the shear stresses. So let's say over here, our x-axis is, let's say, like this, y-axis is like this, and z-axis is like this. Over here, we will have the stresses. Let's say the stress is acting over here. So there will be 2 shear stress components and 1 normal stress component. Similarly, here we will have 2 shear stress component and 1 normal stress component. And also here we will have 2 shear stress component and 1 normal stress component. And now let's see how we define it. You remember it has 2 subscripts, I and j, where I defines the plane and j defines the direction. So if we are talking about this one, so the plane on which it is acting is this particular plane, and this plane is x. In fact, all the 3 stresses here are acting on the x plane, but this is the acting in x direction, this is acting in y direction, this is acting in z direction. So this becomes sigma xx, sigma xy, and this becomes sigma xz. Now here it is the y plane. So the first term would be y for all of these, and then second term will be this one along x, this one along y, and this one along z. So this is sigma yx, this is sigma yy, sigma yz. And here this is z plane, and the 3 stresses are acting in the xyz. So this becomes sigma zx, sigma zy, sigma zz. So what we see here, sigma xx, sigma yy, sigma zz. These are the normal quantities, and therefore normal quantities meaning normal stresses acting perpendicular to the plane. These are the only 3 ones out of these total 9 quantities. So therefore this has the form II. So sigma xx, sigma yy, sigma zz, and so on. On the other hand, the shear stress elements have 2 different indexes. So when I is not equal to j, it is a shear stress, and when I is equal to j, it is a normal stress. And the way it is usually defined or put in the tensor form is like this. Sigma, this defines the tensor quantity, and sometimes it will be written as xyz, sometimes it will be written as 1 2 3. So let me write all the different versions here for sake of completeness, so that in case you encounter any of these, you know that it is representing one and the same thing. Sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Okay, so this is one way to write it, or sometimes people write it in terms of 1 2 3. So it will become sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. And still one more form of representing this is like here. So here in the other one, shear stresses are represented as tau, and the normal stresses are represented by only one index, one subscript. So it becomes sigma x, tau xy, tau xz. This is tau yx, sigma y, and tau yz. This is tau zx, tau zy, sigma z. So what are the few things that we notice here? That the normal stress elements are along the diagonal for all of these. I mean, it is one and the same thing. So normal stress elements lie along the diagonal, and the shear stress elements are the non-diagonal elements. And another important thing to keep in mind is that when we are talking about stresses, positive implies tensile and negative implies. So if the value is given in negative, it means it's a compressive force. It is trying to compress, and if the value is positive, it means it is trying to pull out. So now let's look at one example problem. So it is given that a cubic crystal is loaded with, so let me quickly write down, a cubic crystal is loaded with a tensile stress of 2.8 megapascal, which is applied along to 210 direction. Find the normal stress and shear stress acting on the 120 plane. So the stress is acting along 210 direction, but you have to find the normal and shear stress on the 120 plane. So find So remember that when we are talking about direction, we write it in square bracket, and when we talk about the planes, we write it in this regular brackets. Now to solve this, what you need is a simple refresher of the vector algebra. So if you want to know the angle between two vectors, then we know that it is given by cos theta equal to A dot B by mod of A times mod of B. So here the two directions that we know that we are given are 210 and 120. So this will give us cos theta. Okay, once we have the cos theta, we can find the sin theta from there, because cos square theta plus sin square theta is equal to 1. And these are cos theta and sin theta is what comes into in our equation, if you remember, that we used earlier to find the stresses on a different plane, not the normal to which the stress has been applied. Okay, so with that, we have A as 210 and B as 120. So A dot B would be 2 into 1 plus 1 into 2 plus 0. And mod of A would be square root of A, which will be 2 to the 4 plus 1 square, so root 5. And this one will also be root 5. So this becomes 2 plus 2, 4 by 5 is equal to 0.8. Now, if cos theta is 0.8, then you can easily calculate that sin theta is equal to 0.6. And now that we have the sin theta and the cos theta values, we can calculate sigma y prime, which is the normal stress. And we know that this is equal to sigma yy into cos square theta. So sigma yy is something that is already given to you, which is 2.8. And cos theta is given here as 0.8. So it is 0.8 square. So it comes out to 1.792 megapascal. Now we are going to the shear stress, which is x prime y prime, which is given by sigma yy times sin theta times cos theta. And it is 2.8 into 0.8 into 0.6. So this comes out to 1.344 megapascal. So you can see that once we have established the relation, you don't even need to know how the two angles or directions are oriented with respect to each other. We have derived the normal stresses and the shear stresses without actually going into detail of how 210 and 120 are oriented. But just for sake of completeness, again, I will draw it over here roughly how they would look like. And it may need not be accurate. I'm just drawing it schematically. So let's say this is the 210 direction, along which a stress of 2.8 megapascal was applied. And let's say this is the 120 plane. So if this is the 120 plane, so the normal to it is 120 direction. And what we have found is the theta between these two, which is same as saying that this is the theta. So this is the plane which is oriented at theta, and we calculated that by calculating the angle between these two directions. Now this is when we are talking about x and y axis, but when you have more than two axes involved, then the overall formulation is a little bit more complex, and I will just show you the overall equation, what we need is usually a plane stress transformation, meaning we need transformation along only x and y. So the third axis mostly remains confined, and therefore our relations would become much simpler. However, for the sake of completeness, again, let me just show what we mean by this transformation of axis and what is the full relation to get the transformation from one axis to another. So let's say this is x-axis, this is y-axis, and this is z-axis. And so your system was originally in XYZ, or probably you were doing the calculation in XYZ, but now the different plane that you're looking at is oriented along a completely different axis. So I will draw this over here. I will call this x prime, y prime, and z prime. So these are the three different axes. Maybe your new plane along which you want to calculate is defined along this new green axis, and originally your stresses that you are given or known are along those maroon x, y, and z. So how do we translate? So the relation is very simple, and I will simply, so in a general way, it is represented like this, and the more expanded format for this would be is given over here. So this equation is the compressed or the general format, and this is the expanded format. So here it is giving you what the normal stress would look like, and this is giving you the relation what the shear stress would look like. Now, what are these L terms that are given here? The L terms are nothing but the cosine values between the two axes. So when it says L x prime x, it means the cosine between the cosine of the theta between x prime axis and x. So the angle, whatever angle gets calculated between these two, you will have to calculate the cos of that. So that has to be calculated and squared. So you will get this term Lx prime x square sigma x, Lx prime y square sigma y, Lx prime z square sigma z, and the other terms. So this way you would be able to transform from xyz to another x prime, y prime, z prime, where you have been, your new plane is defined. So now that we have this, let's see if we can calculate a simple relation over here. So the problem that we solved over here. Now, if we look over here, so here what we are given, let's assume that what we are given is along the y-axis. So this is the y-axis. And let's say this becomes the y prime axis. Now, in context of this problem, all other axes are meaningless. What we are interested is only in y and y prime. So when we are talking about the sigma in the other one, so we will be looking at sigma y prime y. So instead of x prime x, we will replace everything by y, or basically rotate x to y, y to z, and z to x. And what we will get is basically just this first term with y prime y. So L y prime y square and sigma y. And what is L y prime y? This is basically theta between y and y prime, which is what we calculated over there, which was cos. So the theta is already known. Theta is something we don't know directly, but we know what we know is the cos theta term. So we were able to calculate this, and this is the same equation that we actually used. The other one that we wanted to find was the shear stress. So tau x prime y prime is what we are interested in, but we have only one term, which is yy. So all other terms would go to zero. This will go to zero. All other terms we can see will go to zero. What remains is only sigma yy. And over here, we want to have two terms, Lx prime y and Ly prime y. So y prime y is cos theta, and Lx prime y, where theta, if you look at it, it is basically 90 minus theta. So cos of that will become sine theta, and therefore it becomes sine theta into cos theta into sigma yy. And therefore what we are getting is that we are coming back to the same equation. But then what you realize is that this is a more general format and you can use it for any transformation. So this is transformation of axis. So we will again now look at another example problem. Here again, we are given the same cubic crystal, which is loaded with a tensile stress of 2.8 megapascal. So cubic crystal loaded with a tensile stress of 2.8 megapascal applied along. So far it is same. Now you are given that you have to find not on the 120 plane but on the 111 plane and in the 10 bar 1 direction. So find the shear stress acting on the 111 plane in the 10 bar 1 direction. And this time we will use the equation that we have derived here. So just for sake of completeness, again I will draw the schematic. So let's say this is a single cubic crystal and this is loaded along this, which is 210 direction, and the total stress here is 2.8 megapascal. And let's say this is your one direction, and this becomes 111 plane. And over here you have to calculate the stress along a particular direction. So it is a shear stress, but not along any particular direction, not along any general direction, but in a particular direction. And what is that particular direction given? That particular direction is 10 bar 1. So now let's go back to this equation. Okay, before that, again, let me define. This is the y direction and this is the y prime direction. And let's say this is the x prime direction. So from over here, what we will get, sigma yy is the only quantity that exists, which is given. All other terms will go down to 0. So we are again left with the same equation, Lx prime y and Ly prime y. So this is again our equation for calculating the shear stress. So tau x prime y prime is equal to okay, I mixed up a little bit. It should be x prime y and coming back Ly prime y. L y prime y is basically cos theta between 210 and 1 and 111, and if you calculate this, you will get √3 by √5, and Lx prime y prime, sorry, it is not y prime, it is y. So Lx prime y is equal to cos theta between 210 and 10 bar 1, and this one will come out to √2 by √5. So tau xy, now we have these two terms, and sigma yy is given as 2.8. So this is equal to √6 by √25 multiplying these two into 2.8, which comes out to 1.372 megapascal. Okay, so what do we learn here? We see that using that equation, we were able to get the shear stress in a very, you can say, we can get shear stress in any direction. And normal direction is, of course, always easy. And shear stresses have various orientation along which you can get. And using this equation, you can get that along any direction. So once you have the direction, you find the cosine value between the two and insert those cosine value into that general equation, and you will have the stress value for that particular direction on that particular plane along any particular direction. Okay, so that we come to close for this particular topic, stress and strain. Actually, we'll keep talking about stress and strain. Stress and strain is a lot more. There are a lot more things to discuss about in this. Next we will be talking about principal stresses. So for now, we will close this chapter and move on.